Math 2415, section 10.7, vector functions. Another eliminating the parameter strategy. In the previous video, we had parametric equations that we extracted from the component functions of a vector function. I'm going to say it again, and I want you to listen closely to the words. We had parametric equations that we extracted as component functions of a vector function. We graphed it by making a table of values, and we also eliminated the parameter. The strategy there was solve one equation for t and substitute it, solve one parametric equation for t and substitute it into the other parametric equation. But I want to graph this one and also eliminate the parameter, but we're not actually going to solve for t. We're going to be a little bit more observant. First, our function that we're going to graph and eliminate the parameter from is okay, that's spelled correctly. R of t is equal to cosine t comma cosine squared t. And from that, we can extract parametric equations, x equals cosine t, y equals cosine squared t. You'll notice I've got a pretty large table of values set up. That's because for this particular vector function, its component functions involve trigonometry, and specifically cosine. So I listed every convenient value of angles on the unit circle that I can put into these functions. Like before, I wanted to start negative and go positive. My thought in having all of these values was based on a unit circle, which you better know because you're in Calculus 3, starting all the way back at negative pi, rotating around until I hit positive pi and made one complete revolution, and stopping at every convenient angle on the way. And if you don't know those angles, even in degrees, you should. And if you don't, how did you get this far? At this point, if you're like, but I don't know my unit circle, I understand, but you need to review it. It needs to be automatic. I'm not going to bother filling it out. But that's where I got these angles from. And I'm going to generate the vectors just like I did before by doing the first components first and then the second components second. So starting at negative pi, cosine of negative pi is negative 1. Remember that on the unit circle, the value of the cosine of an angle is the x-coordinate of its point. Since negative pi is over here, and this point on the unit circle is negative 1 comma 0, that means cosine of negative pi is negative 1. If we continued, we would get negative square root of 3 over 2, negative square root of 2 over 2, negative square root of 1 over 2. Oops, I fell into a pattern, but it would actually work because the square root of 1 is 1, so negative 1/2. And then at negative pi over 2, cosine would be 0 because negative pi over 2 would be pointing down here, and at this point the x-coordinate is 0. Y-coordinate is negative 1, but we're doing cosine, not sine. As we continued rotating around the unit circle, our x-coordinates would be positive. In fact, I'm going to get these values, but just positive until I get back to 1. So 1/2, square root of 2 over 2, square root of 3 over 2, 1. And if you remember that the graph of cosine oscillates, it shouldn't surprise you that it went from negative 1 up to 0, up to 1, and now it's going to start going back down, giving us square root of 3 over 2, square root of 2 over 2, 1 over 2, 0, negative 1 over 2, negative square root of 2 over 2, negative square root of 3 over 2, until we bottom out at negative 1 again. And again, if you don't whip out your cosine values that quickly, that's okay, but you should be able to get them easily. Now, as far as the x-coordinates, well, we just found the x components. As far as the y components, do we really have to substitute all those values in, find the cosine, and then square? No, because we already found all their cosines. Basically, we just have to square the previous answer to get the second components. Negative 1 squared is 1. If I square negative square root of 3 over 2, it becomes positive. The square cancels the square root, leaving a 3, and the 2 gets squared to become 4. We get 3/4. If we square negative square root of 2 over 2, the negative becomes positive. The square cancels the square root, leaving a 2 on top. The square squares the 2, leaving 4 on bottom. We have 2 over 4, which reduces 2 over 4, which reduces to 1/2. If we square negative 1/2, we get 1/4, and of course if we square 0, we get equal 0. We're going to get the same y components down here that we got up there because these are the same x components, just positive. But when we square them, we'll get the same thing. 1/4, 1/2, and 3/4. I keep wanting to say 1/4, 2/4, 3/4 because it makes a nice sounding progression. And then of course 1 squared is 1, and then they're going to go back down again, 3/4, 2/4, which reduces to 1/2, 1/4, 0, and then they're going to go back up again, 1/4, 1/2, 3/4, and then 1. Wait, we're getting some of these vectors more than once. This second vector from the top matches the second vector from the bottom, and vice versa. Interesting. Let's think about what range of values we need on the x and the y-axis, or rather what interval of values. Our first coordinates start at -1, go up to 1, and go back down to -1, which means on the x-axis we only have to go between -1 and 1. What about the y-axis? That's even easier. It starts at 1, goes down to 0, and immediately goes back up to 1, and then down to 0, and then back up to 1. So it only goes up to 1. We might want to subdivide this a little bit more. The y components are easy. They're fourths and halves, so all I have to do is cut that. Now, the x components are not as clear because of the square roots, but we can get decimal approximations. I'm going to cut this into fourths, but those aren't the points. Well, one of them is because of a half. But I happen to know that the square root of 3/2 is approximately 0.86, and the square root of 2/2 is approximately 0.71. You can check in the calculator if you don't believe me. Actually, I do want to check the square root of 3/2. For some reason, my brain's going, no, that's not it. But I don't seem to have a calculator handy. My phone is currently being used to record that, and my computer's not turned on. But so we'll just go with this. 0.71 would be just to the left, or just before 3/4. So we'll say 0.71 is about here, and -0.71 is about there. 0.86 would be somewhere halfway between, let's see, half 20,000. It'd be a little less than halfway between 3/4 and 1. So 0.86, we'll just put it in the middle, is about there, and -0.86 would be there. And of course, a half is right here, so we're not worried about that. That's just 1/2 and -1/2. All right, so let's plot these points. And as I plot them, I'm going to put the t values that generated them, times if you will. All right, -pi. When t was -pi, we were at the point -1, 1. So over here, t equals -pi. Our next point was -square root of 3/2, -3/4, positive 3/4, which is about here. That was t equals -5pi/6. Our next stop was -square root of 2/2, half, so about here. T is equal to -3pi/4. And then at t equals -2pi/3, we're at -1/2, -1/4, so right about there. That kind of looks like a line, but you're about to see that it's not. So t equals -2pi/3 was that. At t equals -pi/2, we're at the origin. So let's put it t equals -pi/2. Then at t equals -pi/3, we're at 1/2, 1/4, so right about here. We'll write it over here. T equals, what did I say, -pi/3. And then at t equals -pi/4, we are at square root of 2/2, 1/2, so about here. T equals -pi/4. At t equals -pi/6, we're at 3 square root of 2 up 3/4, so about here. T equals -pi/6. And then finally, when we hit 0, we're at 1, 1. And those are all the unique points, because notice as we continue, we're just going to retrace the ones we just drew. In other words, at pi/6, I get the same value as -pi/6. So pi/6, and it's going to continue on its way back. Pi/4, pi/3, pi/2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and then finally back to pi. So what's going on here? Well, I started here, and I went this way. Look kind of linear, but it curves and it goes back up. You know, kind of like a parabola. Except this is not drawn to scale because this point is supposed to be a little bit lower. Actually, these are a little bit out of whack. 0.86 would be about right there. Yeah, sorry, I wasn't paying much attention when I plotted these last two, but I fixed them. Okay? And the orientation seems to be from left to right. Now, if you're wondering why am I not putting these arrows on the curve, because what happens when we peaked over there? When we peaked at time equals 0, we're going to start traveling backwards along the parabola. So I'm going to draw arrows pointing the reverse direction on the top side. And guess what would happen when we got back over there? We'd turn around and go the other direction. It's almost like somebody skating a half pipe. We start here, it traces out from left to right. You would think it would slow down here, and it actually, you can tell that it does because the space between consecutive time intervals the length between consecutive time intervals decreases. So you have this oscillation, this, like I said, a skater in a half pipe. You start high, you come down, you go up, and then it slows down and comes back down, and it would just keep oscillating forever. It looks like a parabola, but it can't seem to break free. Well, that makes sense if you think about the trig functions, especially cosine. Cosine's stuck between -1 and 1, which is why it doesn't escape horizontally. Plus, those are getting squared, so all the negatives become positive, and it can't escape between 0 and 1. So why is this a parabola? Well, let's eliminate the parameter. If you eliminate the parameter, the strategy we said before was to solve for t, but I wouldn't do that here. Because another strategy is to look for a relationship between these two functions where you don't have to eliminate the parameter. I think the relationship here is pretty straightforward. Y is equal to cosine squared t. Well, that's literally the square of cosine of t. And our first parametric equation says that cosine of t is x. In other words, if we eliminate the parameter, we get y equals x squared, and it is that parabola. But it would be incorrect to say that this is the equation of that, because this parabola would go forever. That one doesn't. It stops between -1 and 1. So if we wanted to accurately say this is the rectangular equation, ask me in class why I'm calling it rectangular. This is the rectangular equation. However, it's stuck between -1 and 1, so we would have to impose the condition that x is stuck between -1 and 1. And that would be the correct parametric, this is the parametric representation, this is the rectangular representation, but the parametric representation forced this restriction on the x's because of the limitations of cosine. I'd like to do one more video about eliminating parameters, and then I think I'll save the discussion of calculus on vector functions for class on Tuesday. Remember, I did ask you to read as much of 10.7 as you can. The calculus read is actually pretty easy.